Cool. All right. Hi, guys. Welcome to the discussion in week 10. This is also the last discussion session in this quarter for our class. I know you guys have many classes in the final week, and the ECE 113 has so much content. And I really understand that it is easy to get lost in old notes because there are so many things to remember. And sure, so today I'll go through what is taught after the midterm. And given the time limit, I cannot cover everything here, but I'll try to cover all the most important points. And the purpose is to help you have a general picture about the knowledge here, so you can review it more easily. And also, I will go through them according to the lecture order. And you see the blue or cyan color. That means the question scope Professor sent in the email earlier. And yes, to cover them in the lecture order can help you locate the content more quickly during the exam. Cool. So I will start. As you see, in the discussion today, we will first go over, the Z transform very quickly, and we'll see. Let me choose a pretty color. Blue, yellow, blue. Okay, we'll see how they relate to DTFT and its property and the stability. And the stability basically means all the poles are within the unit circle. Okay, and also an important point about the transform is its ROC, the range of convergence. Okay, you need a thorough understanding of ROC and be careful about it. And next, we'll go to LCCDE. We solved the differential equation before the midterm, but here we need to master how to tackle it with the transform. Okay, so we'll turn the differential equation into the transform of our impulse response, and then we do the inverse the transform to get our h of n in the time domain. And here you need the technique, the partial fraction expansion. Okay, and after that we'll move on to discuss the filters. So as you see, the FIR and IIR filters, they are a very important part in our class, but they look so complex, right? There are so many kinds of filters for types, and they also introduce the new concepts like the linear phase, like group delay, phase delay. Yes, and it requires us to read figures, just like the questions in the homework 7. Okay, and yeah, and an FIR filter is even easier than the IIR. The IIR filters, that comes with more uncertainty because of their infinite property, right? And we'll discuss the pros and cons of the IIR filter, and we also discuss the all-pass filter. And the all-pass filter is also explained in the homework 8 problem 5, so it would be a good exercise for you to strengthen our understanding. Okay, and you'll notice that I put M in brackets of FIR filter and N for the IIR. So the basically mean when you design a finite impulse response filter, FIR filter, the most important parameter is M, and M is the length of your window. Okay, because you're using a window to truncate your original ideal filter in time domain, right? But no worry, we will discuss it in more details later. And for the IIR design, the most important parameters is the N. The N is the order of your filter prototype in the in the S domain, or you say the continuous time domain, or you can say the big omega domain. They basically mean the same. So we'll discuss them later. So I put the letter here is to keep you in mind that the design are not that complicated. They basically problems of the parameters. Okay, and the good thing is that we only have one important parameter here. Yeah, and this is basically all the contents after the midterm. Prior to the midterm, we discuss the traditional way to solve the LCCDE, and we also covered sampling. And I know I mean we suffer a lot from the sampling in the midterm, right? You just me interpolated. So I guess after professor's explanation on the midterm exam, we have a better grasp of this part. And the relationship between the DTFT, DFT, FFT is also important. And in a word, DTFT is basically the discrete time version of your CTFT. Okay, and then we sampled it in frequency domain and get DFT, and then we optimize the calculation and we get FFT. And also, DFS is not mentioned here. I will also conclude them in one sentence. So for periodic signal in time domain, we have DFS in the frequency domain, and for the aperiodic, we have DTFT. Okay, so that is the only difference, and these two can actually relate using the so if you also treat the periodic signal as just as a normal signal, you'll see that they are basically the same. Okay, so in the discussion later, I will not have time to cover this part. No, given the time limit. So you can go to check our video for the midterm review, and also spend some time to go through them yourself. And the post midterm exam content is more important in the final, and they will have more points. So it's an efficient strategy. Okay, cool. So we spent about 10 minutes to go through the topics in high level. Any questions before I dive into the first topic? Cool. All right. Thanks for your attention. So I will continue. Okay. So guys, follow my pointer so you won't be confused by so many contents here. Okay. So where should I start? Okay. So we discussed Z transform and its important partner RC. So let's do the exercise about concept. So RC is where x of z is finite. So it is a finite value, finite value. And is finite basically means converges. They're the same, okay? And because x of z, which is a z transform of x of n, right? And it is an infinite sum from minus infinity to positive infinity, okay? It's an infinite sum, so it can be infinite. The x of z can be infinite. So the RC is where we get a finite x of z. You can always check it yourself. And what if x of n itself is already finite? So you can see when your original x of n is finite, x of z will always converge. Why? Because the infinite sum now becomes a finite sum. For example, from 0 to, suppose x of n is non-zero, only from the 0 to big N, and we'll have only a finite sum here, right? So the result will always be finite, except for infinity or 0. Why? Because in your equation here, you encounter z to the minus n, right? So that will create a pole.
What does going outwards and going inwards mean for the RC?
That is the other situation. After we finish this, we'll go to that pretty quickly. Okay. Yeah. So the z to the minus n will generate a pole at 0 or infinity. So when the n is a positive number, for example 1, it will generate a pole at 0, right? And if let's say if the sequence is non-causal and we have negative index, it will generate a pole at infinity, right? So but most of the time for the general z transform, general z domain, the x of z always converges. So I want to remind you about this because the difference of your x of n, it is finite or infinite, will affect your ROC. So So the going outwards, going inwards, apply to the infinite x of n. This is usually ignored, but important. Okay, so
So how do you know whether it's finite or infinite?
sure. So if you only have values like 1, 2, 3, it is finite, right? But if you have a sequence like u n, it is infinite. Okay, and of course you can have a to the n here, so it will continues forever as n becomes bigger. Okay, so when x of n is infinite, and we'll see if it is a right-sided signal or left-sided signal. Right-sided signal, for example, this one, the RC will go in outwards, the outmost pole. Okay, so the Z will be bigger than the outmost pole. Sorry. And for left-sided signal, the RC will within the innermost post. Okay, do I answer your question?
Oh, okay. So going outwards means that it's outside the circle?
Yes, exactly.
Okay.
So the full expression is going outwards from
So
the
right side is
outmost.
Z transform, right?
Yeah, the transform. Cool. Okay, let's continue. And then we comes to the concept how the x of v relate to dtft, which is x of omega. And you can unmute yourself or have your answer silently, doesn't matter. So this is when z equals to e to the j omega, which means z is on the unit circle, it is equivalent to dtft. But yeah, there is a prerequisite, that is the unit circle is within your RC. Okay, otherwise it cannot converge and it will not have any meaning. Cool. And as you see, the DTFT is a special case of the transform, given the value of e to the j omega, and you'll see that their properties are also similar, but all those properties comes with the appropriate changes to your ROC as well, because the x of v, the z transform, and ROC, they are close partners and you can't take them apart. Without ROC, you cannot express the z transform uniquely. So this is something we need to be careful about. But still, we have a way to tackle this trouble. If you guys remember, the z transform has two categories. One category is unilateral, and the other category is bilateral. And unilateral means we only sum the non-negative terms, and bilateral means we sum all of them. So you can see that unilateral is only one-sided, right? And for the unilateral, because it only counts the positive terms, its ROC will only have one case. That is the first case, the right-sided, because by the definition of your unilateral Lie transform, all the signals will be truncated to be a right-sided signal, right? Because it is coming from n to n equals to 0, 1, 2, 3, 4, 5. So it is a right-sided signal, and so it will only have one case. In this situation, we usually ignore the ROC because they're basically the right-sided signal, and by default it will go outwards from the outmost pole, right? So in this context, the unilateral context, we don't need to explicitly claim our ROC. Any question about this?
So I had a question about the prerequisite that you had earlier on the previous page.
Oh, hi, Ara.
Hi.
I just saw your question. The
No,
prerequisite is for
at the bottom of the page.
yeah.
So this is it only for right-sided signals, or is this true for left-sided signals as well?
It is for all of them as well. All of them, as long as your ROC covers the unit cycle.
So for a left-sided signal, does that mean that the smallest pole should be outside the unit circle?
Yeah.
Oh, all right, makes sense. Thank you.
Cool. Okay. So yeah, I hope you refresh you something about the Z transform, and after that, we'll go to the D transforms to see how powerful it is in LCCDE. So for differential equation, we usually have a system not at rest, right? Not at rest means it has some initial conditions. So initial conditions combined with a differential equation is the most common form that we see to describe a LTI system, right? So to tackle the initial conditions, we have to use unilateral Lie transform, okay? So our LCCDE should go through unilateral Lie transform to include our initial conditions, okay? And then we'll get the H of V, and we would like to do the partial fraction expansion, and then we'll get a cleaner format of your H of V so that we can check the table and do the inverse Lie transform. After that, we get H of N. And you know, for the unilateral Lie transform, we don't need to explicitly claim our ROC because it only has one case. It has to be a right-sided signal, right? So the most important part is just we just need to do the inverse Lie transform and get the H of N. And any question about this? Cool. Okay. And to make a diagram here, you know, this is our Qt system, and we have input, we have initial state, and going out of the system, we have many ways to categorize the output, right? And you'll see that I use different color to illustrate. So you can see the input going out of the system. We have two parts. The first part is the forced response, which reflects the input characteristic, which is basically the input pulse. And then the other part from the input is the natural response. And natural response is ignited by the systems itself. So it reflects the system's pulse, okay? And we also have another way to categorize it, which is transient and steady state. So, so as you know, the output is basically an expression of n, right? It may have several parts like this, and then for example, something like this, right? This is just an example. So the expression is the same. The difference is how we categorize all these terms. Okay? So the transient terms are those who decay to zero as n increases. Okay, and if we observe this sequence, you'll see that okay, when the n goes to infinity, this will goes to zero, this will goes to zero as well. So these two are transient response, and this is a steady response. Okay, and if you want to categorize it into forced or natural response, you have to know what is the input, and you see that which term reflect the input pulse and which term reflect the system pulse, so that you can categorize. Okay, so that is the thinking process of it. Any question about this? Cool. And the red color means it only comes from the input, so this is a zero state response, and this is the zero input response. I hope this diagram can help you understand the different ways to think about the output. Okay, I don't see any questions, so I will continue. One more comment here. So the transient response corresponds to pulse in the unit cycle, so they will decay. And the steady state response means we have pulse on the unit cycle, the edge, on the edge, so that it will remain. Okay, and because unilateral, so we can ignore RC here. Cool, awesome. And then so this part, we are going to discuss the system's response to any exponential input or sine or cosine input. Okay, we talk about them together because you know the sine or cosine function, they're just a fraction of the exponential term, right? And they're called the eigenfunction of your system response. Why? Because when the input is sine or cosine or exponential term, the output will have a very obvious pattern that is that is this. So your magnitude response will directly be multiplied to the original input, and your phase response will directly be added to your original phase. Okay, so you can see that the j omega n, the original input, will it will add your phase response at this point. Okay, and your a, your original magnitude, now becomes a multiplied by the magnitude response at this point. So before you do any DTFT or D transform or anything else, take a look at your input. If it follows this pattern, you just need to directly use a conclusion. You don't need to compute the whole process. And similar for cosine, right? You'll see that phase here, the cosine phase directly be added by the phase response at this moment. Cool. And one thing to be careful is this rule, the output you get here, is only the steady state response. What does it mean? It means that if your input, so this input is not multiplied by UN, which means that it is not causal. It is valid across all n value. But in reality, our input is usually causal. For example, if our x of n is a e to the j omega 0 n times un, which means we just plug in the input after zero time, okay? And if this is a case, refer to a diagram here. If this is a case, we will have the forced response as well as the natural response, okay? So depend on what the system is, we might have other things besides the clean output. And what we get here is a steady response. Other transient response produced by the system will go away, will fade away, okay? So so if it only asks you the steady state response or the response after a long time, or if it's or if it told you that your x of n is not multiplied by un, you can directly apply this rule. Any question about this?
Is the second one causal?
Which one?
Xn is equal to a cosine omega naught n plus theta. Is that causal?
This is not causal as well, because the cosine is valid across all the n, including the negative n.
Oh, so both of those two are not causal.
Yeah. So let's say the first case is we know the xn is non-causal, and the yn will be exactly the solution. But if the n given is causal, which means we now have a u of n, the step after the multiply with them. In this case, the yn only represent the steady state response.
Oh,
is that clearer? Any other questions? Cool. Yeah, thanks, Samia.
thank you.
Cool. So that is all about the system's response to our exponential term or sine cosine term. Okay, so we will move to the next block. The next block looks intimidating. We don't usually use these equations or I mean inequalities in our problem. To be honest, their indications, the conclusion it derives, is even more important than the original derivation. Okay. So for the exam, it is more important to understand its conclusion. Okay. And I believe the most straightforward and also the easiest to remember is the third one. Because of this theorem, your h of omega and h of n cannot be time limited or frequency limited at the same time. Okay? If you are limited in one domain, you have to be limitless in another domain. Okay? But you know, in practice, if the side lobe is small enough, we can ignore them. But theoretically, they cannot be limited at the same time. Okay, and the second easier conclusion is this one. So for causal h of n, its phase delay can never be 0. Okay, and this is also very intuitive to understand. so in your real life, if you have a causal h of n, the causal impulse response, it has to have some delay, right? You have to make it convolute with your input after the input comes in, and then you have an output with some delay. Okay, that is why the phase can never be zero. Maybe it is zero. Maybe it is zero at the first time frame, but later, it will be different. Okay, and another important conclusion is this: h of omega cannot be identically zero for causal h of. What does it mean by identically zero? So let's say we have a h of n, and then we turn it into a h of omega, okay? And if we observe a period that is identically zero, which means the function looks like this is identically zero here, then we can know the original x of n is non-causal. Why? Because according to the theorem, if it is zero for a period, continuously zero, the integral here will become infinity. Because when you have zero, your ln zero will be negative infinity, right? And if you take integral of the infinity, you will get infinity. So this will contradict with our conclusion. So the h of n will not be causal. Cool. So you can observe the spectrum and have some indications about the h of n in time domain. Okay. Any question about this part?
For number 3, what do you mean by they can't be limited?
They can't be limited. So limited means that it only have finite supporting. Okay. So it is not. It doesn't have infinite supporting. Which means it is limited.
Oh, okay. So that means finite.
Yeah.
One has to be. You can't both be finite.
Yeah. Oh. Finite in horizontal axis. Cool. Okay. Thanks for your question.
Thank you.
Sure. Well, we are going to talk about the most terrifying part, the filters. I don't know if you agree with me. Okay. So I will first talk about the delay and the phase or the terms for filters, and then I will first go through FIR filter and how to design them, and then I'll go to IIR filter and how to design them. Okay, and in between I will also briefly talk about the minimum phase and the all-pass filter. Cool. So are you ready? Cool. Yeah, I know you're tired, but let's imagine our discussion just started, and this is the first topic, and let's be more.
We're gonna have to race through this in 20 minutes.
Okay, FIR filters and IIR filters. Welcome to our discussion in week 10. We will first talk about the filters. Okay, and I hope you guys already remember the expressions for phase delay and group delay, and I hope you guys understand that the group delay is a most important parameters when we talk about linear phase. Okay, and linear phase is basically unclear sometimes because there is a term called linear phase and there is another term called generalized linear phase, but usually we don't say generalize explicitly, so it will cause some confusion. In the exam, if you are unsure about the term linear phase used in the question, you can always ask the professor, that does it mean linear phase or generalized linear phase? Okay, and what's the difference between these two? So the linear phase is the strictly linear phase response. Okay, and you see when your phase response is the omega times a constant, it is linear. And what you can observe from the phase delay and the group delay is your phase delay will be equal to your group delay and will be equal to n naught, right? Given this equation, you can easily get the result yourself. You get the identical constant, okay? But generalized linear phase means that your phase response is actually not strictly linear. It is affine, right? It adds another constant after that. Let's name it beta. So in this case, our phase delay and group delay, they are not the same, but we still count it as linear phase sometimes. So we are still count it as generalized linear phase. Why? Because it's group delay. The most important parameter is a constant. So we give them the credit. Okay, you are also linear phase, but our phase delay is no longer the same. It will change according to the frequency, but we don't care. Cool. Any question about this? Awesome. Okay. And one thing to remember before we keep going is the restriction to the IIR. So, you know, we usually want a system to be causal and stable, so that we can implement it in reality. Okay. But a causal and stable IIR can never have linear phase. That is bad. And we can compensate it a bit using the all-pass filter, but let's tackle it later. Yeah, it's really important to know the scope before you look for the reference, right? Especially in the final exam. So I will emphasize the scope to apply some conclusion, and I hope it will help you. So as we discussed before, all these terms, they can be applied to any filters, or you say any system, okay? Because they're basically the concept, right? Basically the concept. But remember, we have a conclusion that the group delay equals to n/2. This conclusion is only for FIR. Why? Because the causal and stable IR can never have linear phase. So we narrow down our scope to finite impulse response filter here. Narrow down, okay? And let me check your understanding. An FIR filter is always stable. Is that correct? Mm-hmm.
I think that is correct because its region of convergence contains the unit circle because it's like it always converges.
Cool, exactly. So when we talk about when we talk about stability, we have to think about the unit circle, right? Whether or not it converges, okay? And you know, for the finite, for FIR, it is finite, right? The h of n is finite, so the h of z will be a finite sum, okay? In this case, it always converges. Cool. And another question, is it causal? Let me tell you the answer.
I don't know if it's always causal, but you can always make it causal, right? Like by shifting it.
Yeah, exactly. Because it is finite, so you can always shift it to the right side. So let's say it is causal, and it can be causal if it is not. Okay. And so as we said before, thank you, Edward. So as we said before, we have we are now talking about the FIR filter only, and there are two ways to determine if it is linear. It has linear phase. So the first way is we see that it is symmetric, and we can directly say that it has linear phase. Okay. If it's anti-symmetric, it basically means a affine phase, as we said before, the generalized linear phase. I hope my pace is not too fast, but you know, time is very limited. Okay. And an important point here, always usually ignored, is a causal FIR of order n. It's actually n+1 law, because we count from 0 to n. So it actually have n+1 terms in H domain. In n domain. I mean, H of n is n+1 law. And this is very important, and don't forget it when you are in the final exam. That would be horrible. Okay, and the group delay in this case is n/2. It is only applicable for, you know, the FIR filter because it is derived from an FIR property. Cool. You can look at details in lecture 13. So for both symmetric and anti-symmetric, we have this conclusion. I will continue. And people will ask, we learned 4 types of FIR filter. How does it relate to this knowledge? So I would say that they are basically the same. Okay, the 4 types of filter, they are categorized based on whether the n is even or odd, and the pattern is symmetric or anti-symmetric. So this is all included in this discussion. So the types are basically a more detailed explanations about what is happening within the FIR filter. And because this detailed difference will derive different restrictions at your h of 0 and h of pi using your the even or odd or symmetric properties. So they are all derivable. So no worries, they are the same thing. You just need to refer to the corresponding one given the question content. Hey, wow, our time is so limited. Okay, I'll try to be even faster. FIR filter design. So before the monster, let's remember, we only need to determine the window length and window type. We may need to iterate, but this is basically what we want, okay? Why we need a window length? All right, so for example, we have an ideal filter. All right, it doesn't look like an ideal filter. So in the frequency domain, we probably want a high pass filter, and this is ideal, right? It cannot happen in real life, but let's say it is ideal now. And because it is limited in the band, in the frequency, so we know that it will not be that pretty in the time domain, okay? And actually, it will be a sinc-like function. And the sinc-like function is unlimited, right? It cannot be implemented in the time domain. It is not causal. So we would like to add a window to truncate. So after we truncate the less important part and leave the important part here, we will assume that it doesn't affect the ideal too much, unless add some ripples here. So adding the window in time domain will give you some ripple in the frequency domain. So the ideal filter now becomes non-ideal, but it is still satisfying, okay? So our question is how to determine the length of the window. The longer the window, the more accurate the approximation is, right? But we also know that the longer the window, you require higher order filter, and it is not good. It is not easy to implement. So we want to balance. We want to find the ideal window type and the ideal length to tackle it. But what is the problem? The problem is for the FIR filter, the original ideal phase, ideal pattern in the time domain, it can be anything, right? So we have to iterate. We have to do some iterations to find a property M according to our experience. Cool. So this is basically the general picture, the general step, and let's conclude it with text. Okay. So the first step is to select a window. If you don't know which window to select, don't worry, because it is easy in MATLAB, right? All the other code are the same. You just need to change the window. If this window doesn't work, change another window and see if it improves the frequency response. Okay, select a window, and then you need to know what ideal filter you want to implement. You want to implement low pass filter or high pass filter, whatever. So you first need to know what is your ideal h of omega. Okay, let's say, and then we would like to turn it into h of n, right? And as we see, the h of n of an ideal filter is not time limited. So we want a window. We can first guess what is the m, guess the window length, okay? And then how to make the guess? So we have two ways. The first way is to check the main lobe, side lobe, and other specifications of that filter, of the window you choose. And you'll see the similar chart, the similar table in the lecture. Another way is to use the empirical rule. And the rule is the number of tabs. So the number of tabs is basically m, and it is basically your order of filter plus 1. Remember, we discussed a causal FIR filter of order n is m plus 1 long, right? And for the window, it is similar. So when the window is big M, the window itself can also be counted as a FIR because the window is finite in time domain, okay? And then let's just use n, okay? And this n is not anyway. So when you apply the window of m length, the original FIR will also be truncated to have the length of m, right? So the order will also becomes m minus 1. Anyway, but I put an N here is misleading, so let's still use M. Okay, so this is by the engineering experience, it is approximate to the attenuation, which is in dB here, over 22. I don't know how the 22 comes from, so this is the experiment. I'm sure cool. Okay, so the F here, their unit is cycle per sample. It is a small f, so you need to do some conversion. So by this mean, we get an M, okay? So we have anything we need. The next step is to multiply the window in the time domain. So let's say we truncate our original HM to be truncate version HT of n equals to h of n times the window. Okay, and then as Edward said, we want it to be causal, so we shift it a bit. We delete it to the right side to make it causal. Cool. So now we have everything. We already have the truncated ht of n. So we want to turn it into a frequency domain again. So it becomes ht of big ht of omega. Okay, and then we want to check if it meets the specification. Okay, so we want to plot it and to see, okay, if the ripple is within our prerequisite, if the ripples in the stop band is within our requirements. Okay, so this is the checking. If it works, that's perfect. You design a filter just at one glance. Okay, but if it does not work, do it iteratively. What does it mean? It means we need to change the M a bit, or we need to change the window type, whatever. So this is the try and error, and then until you meet the specifications. Okay, so you'll see that the FIR filter design is kind of an art, right? Handcrafted art. You need to try yourself and finally gets your result. But this is the way to think about it. So I noticed that the time is up, but I still want to continue. The people who are very busy, please check the recording. I'm so sorry, the content is just too intense. Okay. And then any question about FIR filter design? Cool. And for the IIR filter, we said that FIR filter has many advantages. Okay, it is by default causal and stable. But why should we still use IIR filter? Here comes the pros of your IIR filters. First, it has lower order given the same specification. So the lower order means it's easier to implement, and there are fewer chance to have your overflow error, your approximation error, and all kinds of stuff. Another advantage is it has analog filter legacy. So unlike FIR, you need to do a lot of try and error. IIR has analog filter legacy, so you can make use of its the explicit expressions to accurately get the parameters you want. Okay, so I'll talk about it later. But one problem is that IIR filter, if it is causal and stable, it cannot have linear phase, right? This is a big problem. So how to fix its phase response? In other words, how to make it linear? And the solution is all-pass filter. So maybe we cannot solve it completely, but all-pass filter can, to a large extent, alleviate the situation. Okay, so I would like to refresh the all-pass filter concept really quick. So we learned all-pass filter in the lecture when we talk about the minimum phase. So the minimum phase is not that related to the IIR filter, but it is also important. So let's just briefly refresh on this. So minimum phase means that h of d as well as its inverse, which is 1 over h of d, let's name it h inverse of d. They are both causal and stable. In other words, all zeros and poles of h of d are within a unit circle. In this way, even you flip it, the zeros and poles are still within the circle, right? That's why it is always stable. And the reason we call it minimum phase is that we notice that the systems who has these properties will always have the minimum phase. And or you can say the minimum group delay. Okay, so minimum phase systems are usually called minimum group delay systems. Okay, but the minimum group delay doesn't mean the group delay is a constant. Sometimes it is still a curve group delay. So you can see that it is minimum compared with the systems with other properties. So the group delay is a minimum, but it is not guaranteed that it has linear phase. So you see that these two topics are not that overlap. Minimum phase is minimum phase, and linear phase is linear phase. They are different. And so we discuss minimum phase for the systems that we cannot reach linear phase, but we still want to optimize it. Okay. So usually we want to optimize the non-minimum phase to minimum phase. And how do we do that? We use the all-pass filter. So in this example, we decompose the non-minimum phase into a minimum phase times all-pass. But in reality, we usually do the opposite, which means we want to cascade the non-minimum phase with an all-pass filter, and then we turn it into the minimum phase. But you can do either way because this is just a illustration of the concept. And so in the domain, we can write it in this way. So we will have the group delay of the non-minimum phase system equals to the group delay of the minimum phase system plus the group delay of the all-pass filter. And you see that it because the group pass filter is always bigger or equal to 0, so your non-minimum phase group delay is always bigger than the minimum phase delay. So this also counted as a proof to show that the minimum phase has minimum group delay. Okay. And as for the all-pass filter, it is basically any filter that the magnitude response is 1. Okay. So its phase response can be anything that can compensate your original filter, but its magnitude is always 1. What does it mean? It means that an all-pass filter will never change your magnitude response. It will also change. It will only change your phase response. In that way, it can be designed carefully to compensate your unsatisfying phase response. Does that make sense? So as we see here, similarly, we can also choose a kind of carefully designed all-pass filter to times it with our nonlinear phase system to get approximately linear system. So it is fine as long as you understand the concepts. Okay. In the lecture, we also don't spend too much time covering the calculation detail, but there's a kind of all-pass filter that can compensate the linear phase. And I will, like I said before, I recommend you to carefully do the problem 5 in homework 8 to see if you're understanding all-pass filter correctly. Awesome. So this is the last block of the whole discussion. Let's finish it quickly. So as we said, IIR filter has advantages in its own aspects. So let's talk about how to design IIR filter, and keep in mind the difference between IIR filter design and FIR filter design, and you'll see why people don't give up on IIR filter. Okay, so the main difference here is we would like to tackle it in analog domain, right? Even though IIR filter is not in analog domain, but we want to change it to analog domain to finish the design, and then we digitize it back to use it in the digital context. Okay, so the step 1 is change all the specifications to analog domain. And in the previous discussion, we talked about how to do it with our Butterworth filter. Okay, and in that problem, if you guys remember, we do this transform, not transform, it's just a conversion. We do this conversion, and where f is offered in the question and in the units of hertz, but we want this. This is the big omega, the rad per second is what we want in the analog domain. So we do the conversion. But what if the question give us omega? So for omega, the conversion is like this, okay? And the unit of omega is rad per sample. So we use this equation to convert from omega to small omega to big omega. And the omega can be the stop band omega, the pass band omega, and the 3 dB, the cutoff omega. Okay, it depends on what the filters you're going to use and what specifications are given in the question. So correspondingly, the small omega will also be omega cutoff, omega pass band, and omega stop band. Okay, great. And after we get the specifications in the omega domain, the analog domain, we would like to design it in the analog domain. And keep an eye on this. So h of omega and h of s, they're basically the same. Why? Because s and omega, they're just different by a j. Okay, so when you see this equation or this equation, they both refer to the design in analog domain. So it is not a contradiction. Cool. And then we choose a prototype. And the prototype means the type of filter you want to use in the analog domain. So you'll see that here, our filter is built upon the prototypes, right? It is not like applying a window to a strange signal. In this way, we have the 4 expressions of the filter we want. So we can explicitly calculate the parameter we want rather than trial and error. Does that make sense? Cool. So the prototype basically means the types of your filters. For example, the Butterworth we discussed before, and the Bessel, and the Shabby, blah, blah, blah. So all of them, the equations are listed in the lecture notes, and there's also figure comparison about their difference. For example, the Butterworth, it has higher order, but it is smooth in both passband and the stop band. And Shabby, there are 2 types of them, and one type, so type 1 has ripples in the passband, and the type 2 has ripples in the stop band. So you need to observe your specification and see if it has higher requirements of the passband or stop band or both or neither, and then you go to select select the filters that match your requirements best. Okay, so it is not that difficult. It is just a first conversion, and then choose a filter according to your specification, and then what should we do? And then we need to digitize it. We need to turn it from analog domain back into our digital domain, okay? And the digitization is also not that difficult. There are 2 ways to digitize it. The first way is by linear transform, which is the most common way. The other way is impulse invariance, which is less common, but still popular, okay? And you can see that they're basically using different equations. For bilinear transform, we just want to, we finish design in S domain, and then we let S equals to something, and then we'll get the H of D, and then we want to turn the H of D into H of omega, so we get the DTFD of our filter. And that's it. We are all done. And the second way is impulse invariance. This is a little bit troublesome, but still straightforward. So we have the equation in S domain, and then we want to do inverse Laplace, and we get it in continuous time domain. And then because we want to digitize it, we take sample in time domain, and we get our discrete H of n. All right, and then we we turn it into our H of D or H of omega. It depends on what you want. Okay, and these are 2 different ways, and you see that the method B is more strict. Why? Because in method A, this value is actually an approximation. Okay, it is not the exact value; it's just an approximation. So it will hurt it a bit in the group delay. So so if you check the lecture notes, you'll see how they get this approximation. But I believe it is not required in the final, or it would be too crazy. And because of the approximation, A is worse on the group delay, but it is preferred for its convenience and simplicity. So you can check the comparison diagram of method A and method B in lecture 16, and if your bilinear transform cannot satisfy your requirements, the design requirements, you can also try the method B. Perhaps you can get a better result in your group delay. Okay, wow. thank you for being here. I know it's a long discussion, and I hope you can save you a bunch of time in preparing the final exam. And that's the end of the discussion. Thank you very much.